So let's look at the 3D shapes of the orbitals and nodes. So what we remember, we use certain terms to describe these orbitals. So due to the wave-like nature of the electron wave functions of orbitals, there's going to be areas of constructive interference, additive maxima, and destructive interference, where things cancel in their minima, right? This is just because of the properties of waves. All waves behave this way. So the wave function maxima are going to be the regions of the highest probability of finding the electrons. An important classification tool in this is the idea of a node. And there are certain locations in, around a nucleus where you will actually have 0 probability of finding an electron in that orbital. It's sort of weird. You could divide the shape into divide space into 2 different shapes that really have no connection between them, or they're connected at a single point, and somehow the electron is hopping back and forth between both of them. It doesn't really go in between, it's just in both places already. So the waves have these weird functions that they look disconnected, but they're all still one orbital that can be occupied by an electron. So the maxima, nodes, and the geometries in space sort of define these orbitals. So let's take a look at the simplest, the 1s orbital. And it is perfectly spherical. There is no angular dependence. It looks the same in the x, y, and z direction. And so if we plot the wave function squared as a function of distance, the probability is highest at 0 and then decays exponentially. And it literally is exponentially. It's an exponential function. We'll look at the shape of Schrödinger's equation, the solutions in a little bit after we get more comfortable with the shapes. Yes, the height of the curve is proportional to the probability density. Now, an important thing to remember, where is the probability of what volume of space does the electron spend the most time? It's not really quite spending the most time, but where is the electron the most? It's not actually at the origin. And the reason for that is, if you look at the volume that has very small x, y, and z, it's actually quite a small volume. As you get to bigger and bigger radii, then there's more volume in that space. And this is something, if you're taking Calc 3, you'll get this drilled into your head. You're getting it drilled into your head. If you haven't, you will soon. That if you look at the total probability in the shell at a given radius, it's going to be the probability density at that point times the volume of that thin shell of matter, which is equal to 4 pi r squared times the thickness of that shell. So you can think about it in 2D. You have think about in let's go back to looking at this. If you look in 2D, then you have a shell that's one shell, that's another shell, that's another shell, and as you get to larger and larger shells, they have more and more volume. And that's exactly the same idea looking in 2D. So here is actually the total probability as a function of radius. There's actually essentially zero probability to see it at r equals 0, because there's simply no space for which r equals 0. In 3D, as you get larger and larger, there's more and more volume associated with each cell. So the total radial probability actually peaks at 52.9 picometers. That's 0.0529 nanometers. So the most probable location is at that maximum, and then it gradually dies off. The shell volume keeps on going up with volume, but the probability density goes down faster than that. So you get this peak in the probability. So there is the radial distribution function of the electron probability, which is a product of how much space there is at a given distance from the center and the probability density from Schrödinger's equation. So those are when you look at graphs of probability density, you should be clear whether you're looking at the graphs of probability, whether it's the probability of density, the probability per unit volume, or it's the total probability. Because in this case, the probability per unit volume is highest at the center of the sphere, but it is, there's no volume at the center of the sphere. So the total, you're most likely to be observing the electron at 52.9 picometers. Okay, so that's how we think about the probability distribution within the simplest orbital, the 1s orbital. Let's now look at the 1s and the 2s orbital. So here I've got the general shape of the orbital. And usually when you see a cloud, remember, if you look at this graph here, you can see that although it decays exponentially, there in theory is the probability of seeing the electron like, you know, a nanometer away from the radius, from the nucleus. It's pretty small, but it's possible. So the spheres are not like the shell in which all the electrons are enclosed. It's sort of like, you know, within the sphere, we're enclosing 90% of the probability density. And then 10% of the time it could be outside that shell. So they are suggestive of most of the probability, but it's not the entire probability. You could, you know, very easily have an electron influencing things, you know, a nanometer away, 2 nanometers away. It would be very rare. More than that would essentially be impossible. In theory, it could happen, but you know, it's just too rare to actually occur. But yeah, so that is what we mean when we plot the shape of the orbitals. Okay, so let's look at the 2s and the 3s orbitals. So what do we see? Let's focus on the probability density first. You can see that the probability density starts out large at r equals 0, just like for the 1s orbital, goes down, and it reaches a node right here. So that is a node where it has exactly 0 probability. See these two regions where it has high probability with an area in between where it has no probability of being. So the electrons can essentially be in both places at once because of the quantum mechanics. An important thing here is that I've added some phase information here. So blue means that there's high probability and white means there's low probability. But the wave function itself, remember the probability is the wave function squared. The wave function itself actually goes back and forth between positive and negative. So it's for the 2s, it's positive in the middle, and then it goes out to negative. But if you square a negative, you get a positive again. So this region here, the wave function's positive. This region's here, the wave function's negative, but the probability is still positive everywhere. Where do phases matter if they don't matter for probability? It turns out that when you add orbitals together, things that have the same phase are additive, and things that have opposite phases cancel out. And that'll come in very handy when we look at bonding. But for single orbitals alone, it doesn't really mean anything. It's just, you know that if it goes through a node, that it switched from positive to negative phase. But negative phase still means probability. Positive phase still means positive probability. If we look at the total probability distribution, you can see it's much more likely to be observed in the outer regions, just because there's more volume there. As you could probably guess, the 3s orbital, we now have 2 nodes. There's 2 nodes here. And so there's 3 regions of probability. It actually goes from positive phase at the center to negative and back to positive. Each time it crosses a node, it switches the phase. So that's what 3s looks like. And you could probably sit right down and draw a 4s curve of what the radial density for a 4s probability distribution would be. That would be, you just keep following the patterns. How many nodes does a 4s orbital have? Well, it's going to have 3 nodes and 3 nodes in the radial direction. How about a 5s orbital? 4 nodes. It'll just keep wiggling like that. So that's what the s orbitals look like. They are uniform in space, but as you go up to higher energies, the electron density gets pushed out, right? Let's look right here. We can see that most of the electron is spent in the 1s orbital. It's spending most of its time, around about 53 picometers. Here it's actually spending its time at about 300 picometers, and here it's spending its time out at about 700 picometers. So the electron is moving out as you get to higher and higher as you get to higher and higher quantum numbers. And these orbitals are also higher